Hello and welcome. In this video, we're going to talk about slope fields and how to create them. Slope fields are a tool that is used to help us visualize the solution to a differential equation that we may not be able to solve using methods in this class. So let's go ahead and jump right in. So the idea of a slope field is that sometimes we're going to run into differential equations that we can't solve using the separation of variables. And if we can't solve them using the separation of variables, but we still want to talk about what their solutions might look like, this gives us a method for doing that. We will look at how to create slope fields and how to look at a slope field and sketch a particular solution. Just like in the last video, we were able to talk about general solutions and, if we had an ordered pair, a particular solution. So keeping in mind that a derivative is the slope of a tangent line, it should make sense for us to think about a differential equation as a bunch of different slopes to tangent lines, or a differential equation is a model of the slope because it's modeling the derivative. So if we looked at a specific equation here, y prime equals 3xy, we could find the slope, because that's what a derivative is, we could find the slope at a variety of different points by plugging in a particular value for x and a particular value for y. So for example, if we wanted to know what the slope was at the point negative 2, 2, we would plug in negative 2 for x and positive 2 for y, and we would get that the slope at the point negative 2, positive 2 is negative 12. So the idea in a slope field is that we talked about earlier in the year how the more and more tangent lines we have, the better an approximation we can get. So locally, or close to a particular value, tangent lines do a really great job of approximating the shape of a function. That's the whole idea of local linearity. So it stands to reason that we should be able to get an idea of the shape of a graph if we just sketch a bunch of little tangent lines in a coordinate plane, and that is called a slope field. So sketching a bunch of different slopes at particular ordered pairs is what a slope field is. It's a graphical representation of the slopes obtained from different xy coordinates in a differential equation. Now, all that sounds a whole lot more complicated than what it actually is. So let's go ahead and look at an example here. We're going to look at the differential equation dy dx equals negative x over y. And we're going to find the slope at each of these ordered pairs below. So if I plugged 3, 2 in, I would get negative 3 over 2 would be the slope. If I plugged negative 1, negative 3 in, I would get negative 1/3. If I plugged negative 2, negative 1 into dy dx equals negative x over y, I would get negative 2 over 1, or negative 2. And last but not least, if I plugged in negative 2, 2, I would get 2 over 2, or 1. So what we just identified is at each of these 4 points what the slope is. So if you look down below at this, it looks like an XY coordinate plane, but it has a bunch of little dots. These little dots are for each of the individual slopes. So on top of every dot, you're going to put the slope, and that slope represents what we would get at a particular value. So for example, and this is actually part of the slope field for this differential equation that we just found. So I'm going to rewrite that below. This is the slope field for dy dx equals negative x over y. That's what this is the slope field of. So we're going to finish filling it in. We're going to fill in all of the different slopes that are not already there. So if you see a dot that doesn't already have a line through it, we're going to add the slope there. So let's actually start with the ones that we just found for A, B, C, D. At the point 3, 2, so over 3 up 2. Oh, actually, we can see that slope already. So at the point 3, 2, we can see right here that there is a slope mark that is approximately negative 3 over 2. So one thing that you should be asking yourself is, how in the world am I supposed to know what the slope negative 3 over 2 looks like? And I'm going to try and help you, and it's going to be a little harder on a device here, but I'm going to try and help you see how you can use a ruler to do a really good approximation of those slopes. Okay, so I just found out that the ruler feature in here, you can't see the ruler on the screen. So I'm going to go about this a little bit differently. If we are looking at the point 3, 2, where is that point? 3, 2, right here. This is saying we just calculated that the slope should be -3/2. And I really want you to think about that in an algebra 1 way. That would be as if I went to get to this point down 1, 2, 3, and to the right 1, 2. And I connected using a straight edge those dots. So that's what this little teeny tiny tick mark or little piece of a line looks like. If we look at the point -1, -3, so -1, -3 down here, the slope at that point should look like -1/3, meaning to get to this point, it should look like I came from over here, I went down 1/3, and it should look like I connected those two dots. So if you actually have a straight edge, which you should be using here, you can make that connection using your straight edge. So you're just drawing a little tiny piece of a line. At the point -2, -1, so this point right here, the slope should be 2. So it should look like I came down 1, 2 over 1, and that's exactly what that looks like. So you're drawing little teeny tiny slopes using a straight edge at each point. At the point -2, +2, the slope should look like 1. So -2, +2, it should look like I'm going up 1 and over 1, that I'm connecting these two dots. That's what that little slope is representing. What would happen if y was equal to 0? So thinking about dy dx, y is not allowed to be 0 because then the denominator would be undefined, or the denominator would be 0, so the fraction would be undefined. So dy dx is undefined, or does not exist, at y equals 0, which means everywhere where y is 0, which is all along the x-axis, there will be no little tick marks because the function doesn't exist there. The differential equation doesn't exist there. What about if x is equal to 0? If x is equal to 0, what happens to dy dx? Well, dy dx is -x over y, so that will always be 0. So I can go all along the points on the y-axis where x is 0, and I can draw a slope of 0, which would just be a horizontal slope, right? There's no rise or run. We're just have a slope of 0. We're going to find the slope of all of the dots that don't currently have little tick marks on them to complete this slope field. So what I'm going to do is I'm going to make a table, and I'm going to just start at the left and do all of the ones for where x is equal to -3, and then move to the right, and just any dot that doesn't have a little tick mark on top, I'm going to finish off the slope field. So let me set up a table to make it easier to see what I'm doing. So I know I'm going to have to add more points here, but there are 4 values where x is equal to -3 that we need to find here. So if x is equal to -3 and y is equal to +3, and I plug that into dy dx equals -x over 3, I'm going to get 3 over 3, which is 1. So if I go to my graph at the point -3, +3, it should look like I'm going up 1 over 1 when I draw my little slope. So you can use your straight edge to draw that slope. At the point -3, 1, if I plug that into -x over y, I'm going to get 3. So what that means is, to graph this slope, it should look like I'm going up 1, 2, 3, and over 1. So like I'm connecting a line here. So it's going to be sharper. It's going to be, or steeper, I guess you could say, than the one that we just drew, because 3 is a bigger slope than 1. If we plug in -3, -1, we're going to get a slope of -3. So when I come down to this point here, I'm going to be thinking down 3 to the right 1, like I was connecting a line here. So very steep, but now with a negative slope. And -3, -3 is going to have a slope of -1. So that's going to be as if I was connecting like these 2 points, right? That would be down 1 over 1. But I need to draw a slope that looks just like that at -3. Okay, I need to figure out what happens when x is -2 and y is 1. When x is -2 and y is -2. So let's go ahead and fill those in. So if x is -2 and y is 1, my slope is going to be 2. If they're both -2, my slope is going to be -1. So again, I'm coming over to this point. My slope should be 2, so up 2 over 1. So line your straight edge up with these 2 points from here to here and just draw a little tick mark, a little line. At -2, -2, I should be lining it up, -2, -2, lining it up like this so that I could connect these two pieces with my straight edge to get a slope of -1. We're going to do just -1, x equals -1 together, and then I'm going to encourage you to pause the video and work through the rest on the right-hand side on your own. So if x is -1, we need to know what happens when y is 1, and -1, -2. Those are the two dots that aren't filled in yet. So if x is -1 and y is +1, that's going to give me a slope of 1. So again, it's like I'm connecting these two places here with a straight edge. If x is -1 and y is -2, my slope is going to be -1/2. So here, it's like I'm going down 1 and over 2. So I would draw a connecting piece here, not connecting the two dots, but as if I was, a little tick mark. So go ahead and pause the video and try and work through the slopes on the right-hand side on your own, and then unpause the video to see how you did. So hopefully you had enough time, and making a table is it's sort of a frustrating way because it takes a while, but it is a good strategy for creating a slope field. Now, if we were asked, and actually I would ask you, what does this graph look like? What does it look like it's focusing on? What kind of shape do you see within? And I'm hoping that what you kind of see, it looks like a circle. Except remember that y equals 0 line, that x-axis is like a no-go zone. We can't cross that area. So what's happening is sort of semicircle looking pieces. If we were to sketch a particular solution, which I'm going to do in highlighter so you can see it a little better, if we were to sketch a particular solution through a given point, then we need to make sure that we don't cross the x-axis because the curve is not defined there. So at the x-axis, we would have an open circle. So when we're sketching curves, we're basically like bowling with bumpers. We want to make sure we go through the point that they specifically tell us to go through. And then we just want to sort of follow the flow of the slopes, not really crossing or making too dramatic of turns. Again, this is sketching, so it's not precise. So if we were to sketch a solution that passed through the point -1, 1, so I want to make sure that I go through this slope here. When I get to the x-axis, which I don't know, somewhere around here, I want to make sure that I have an open circle, and I want to make sure that I have an open circle on the other side. And then we're just really trying to connect and sort of stay between the lines. If we were to do the same thing, passing through the point 0, -3, again, I'm going to curve this way and this way. I'm just sort of trying to stay between the bumpers, and then I want to make sure when I get to the axes that I have open circles. So those would be two separate particular solutions. Now I want to show you one more thing on this problem, and that is that we actually know how to solve this differential equation. So let me clear some space, and then we're going to review what we covered in the last video and solve this differential equation. So if dy dx equals -x over y, we can separate our variables. Y dy equals -x dx. And then we could integrate both sides. So y squared over 2 equals -x squared over 2 plus c. We could multiply both sides by 2. So y squared equals -x squared. I'm going to change the subscript on my c. And just like we did last class, we can square root both sides to give us two separate solutions. Either y is going to equal the square root of x squared, -x squared plus c1, or it's going to equal the opposite of that. So you can see that the purple particular solution we just found would be using this top equation, which makes sense. The green solution would be using this bottom equation, just like we did last class. But now we're getting a visual idea of what this would look like. Now, if this was our differential equation, it obviously makes more sense for us to just do the math and solve it, but that strategy will not always work for the types of differential equations that we're going to see. So what we're going to do in the remainder of this video is we're going to practice a couple more times sketching some slope fields, and then sketching particular solutions. And then we're going to actually look at a slope field that's given and try and identify what that slope field is, or what information we can find from that slope field. Okay, let's keep going. Okay, for number 1 here, we are given the differential equation y prime, or dy dx, equals 1 over y. So something I want you to notice about this differential equation is that the y value determines everything. There's no x in the function at all, which means if we were going to make a table to find our values at different ordered pairs, we really just need to plug in our y values. So since this graph goes all the way up to 3 and all the way down to -3 on the y-axis, I'm going to include all of those numbers. If I plug 3 into this equation, I get 1/3. I get 1/2 if I plug in 2, 1 if I plug in 1. If I plug in 0, this doesn't exist because 1 over 0 is undefined. If I plug in -1, I get -1. -2 gives me -1/2. -3 gives me -1/3. So I was taking all of these y values and plugging them into this differential equation. And now I'm going to graph those slopes. So everywhere that y is 3, which is all 1, 2, 3, 4, 5, 6, 7 of these top points, obviously this would go on forever, but on our graph, there are 7 points where y is equal to 3. All of them are going to have a slope of 1/3, meaning I'm thinking to draw my little slope lines that I'm looking up 1 over 3 or down 1 over 3 to try and get that angle, right? So I'm using a ruler or a straight edge to give me the right angle for my curve. So 1/3 is going to look not super steep. And I'm doing the best I can without a straight edge here. Those are my little tick marks for 1/3. Now 1/2 is going to be a little bit less steep. It's like I'm going from 1 point down 1 over 2. So it would be like I was connecting these 2 dots together with a straight edge. But I need to do that for all the lines where y is equal to 2. All the way across. If y is equal to 1, the slope is 1. So that's as if I was just going up 1 and over 1. So as if I were connecting these 2 points together. So 1. I'm going to leave the x-axis completely blank because, as we said, when y is 0, this differential equation is undefined. And then if I go below the axes, I'm at -1. So now it's like I'm connecting down 1 over 1 on each of these lines, down 1 over 1, as if I was connecting these 2 dots to make a little slope line. So -1, -1 is the slope for each of these points. And then down 1 over 2, down 1 over 2, so as if I was connecting, down 1 over 2, as if I was connecting these 2 points to get the slope for when y equals -2. Here we go. And then lastly, -1/3. So this is going to be the smaller the fraction is, or the larger the denominator of the fraction is, the more flat this is going to look. So down 1/3, it's going to look almost like we're just getting really flat with our slope here. And all those blue ones in the bottom row should be exactly the same. Obviously, I am not perfect, especially without a straight edge here, but you're getting the basic idea of the shape. Now, remember that this graph never crosses the y-axis, and this kind of looks like a wave, or maybe like a part of a parabola that opens sideways. Let's see what happens if we sketch the particular solutions. So if we sketch the particular solution through the point -2, -1, so I need to make sure it goes through this slope. I also need to make sure that when it gets to the y-axis that there's an open circle. So I'm not sure exactly where it's going to cross the y-axis, but I know it's going to pass through this slope, and it's going to keep curving in the same way that the slopes are curving. And I'm just kind of trying to stay in between the different slopes that are there. It never goes above the y-axis. And then for 2, 2, if I was going to plot that one, I need to make sure that goes through this slope up here. It's going to go towards the y-axis, and it's going to hit there with an open circle, and then it's going to just kind of keep going along the curve that it seems like those slopes are creating. Think about it like a current. We're just tracing the path along the bumpers or along the current of the waves. We could solve this differential equation. dy dx is equal to 1 over y. So y dy equals 1 dx. We could integrate both sides as we did in the previous section. So we would get y squared over 2 equals x plus c. And if I solved for y here, we would get that y is either the square root of x squared, 2x squared. If I multiplied both sides by 2 plus c1, or y equals negative the square root of 2x squared plus c1. Which again makes sense. This is a lot like the one that we just did. There's a reason that y can never be 0. 0 is the dividing line between using this function versus this function. Okay, we're going to sketch one more differential equation together, and then we're going to look at one that's already been created. All right, before we jump in, I'm going to have you change number 2. This should say sketch the particular solution through the point 2, 2. Since the point that was already there, it's not actually going to be in our slope field. So graph the slope field for y prime equals 1/2 x squared. So y prime equals 1/2 x squared. What you're going to notice here is that unlike the one we just did, now y doesn't matter. So I can make a table with my x values, -3, -2, -1, 0, 1, 2, and 3. I can plug each of those x values into the table to find the derivative values or to find my slopes, and then I can graph my slopes. So go ahead and pause the video to fill in this table, and then unpause the video to see how you did. So hopefully you had time to work through this. And this is a symmetric one, which makes sense because the graph of the derivative, the differential equation, is a quadratic. Now 9 over 2 is going to be really hard to try and graph that slope even with a straight edge. It's almost going to be vertical. So just do the best that you can. This time we can cross the y-axis or the x-axis because x is allowed to be, or y is allowed to be 0. And this is the exact same slope on the other side. I'm not doing a great job of making those look identical, but I think you get the picture here. When x is 2 or -2, the slope is +2. So we're thinking up 1 over 2. So go ahead and pause the video and add those slopes in. And then go ahead and do 1/2 and 0 as well. So just fill in this slope field and then unpause the video and see how you did. So for +2, I'm thinking up 2 over 1. So it's like I'm connecting these 2 points here. And I'm thinking that as I go all the way down, same thing over here. And again, if I had a straight edge, I would be actually lining it up for each little slope tick mark that I'm making. For +1 and -1, the slope is 1/2. So that's as if I was taking from here down 1 over 2. So I'm connecting these two. So it's going to be a little flatter. Same thing over here. And then when x is equal to 0, the slope is 0. So we're going to have horizontal tick marks here. Go ahead and pause the video and try and sketch the particular solution that passes through the point 2, 2. So that passes through this point here. So remember, we're playing the bumpers game here. We're trying to stay in between. So all of these slopes, until we get to 0, all of these slopes are increasing. Once we get to the x-axis, it looks like I'm starting to go kind of curve down this way. This should be more fluid, but I'm doing the best I can here to give this shape. That should make sense if you think about if we were to integrate this, we would get x to the third. with some sort of scalar in front, but this does sort of look like a cubic graph. If I had done a nicer, smoother curve, it would definitely look more like that. We're not going to take the time to solve this differential equation here, but if you need more practice on that, check out the video before this. What we are going to do now is look at a slope field that's already here and kind of identify some key attributes about it and figure out what that function might be, and then we're going to wrap up this video. Okay, here we go. Here we have already been given a slope field. So we have a slope field. We're trying to figure out which of these differential equations could this slope field be. So a couple things that I will look for first is there anywhere that it's not defined? Is there anywhere that there's not a little tick mark? And in this case, it looks like there's a little slope drawn at each of those values. The next thing that I'm going to look for is I'm going to pick something easy to identify. Usually using 0 is pretty helpful. This point right here is the point 0, 0. And I'm going to look at that and kind of decide what it seems like the slope is there. Well, it looks like if I extended this out that it would just hit right here. So it looks like it has a slope of 1. So we're saying at the point 0, 0, y prime should equal 1. And I'm going to check that. If I plug 0 in here, do I get 1? No. So it's not going to be A. If I plug 0 in here, do I get 1? No. So it's not going to be B. If I plug 0, 0 in here, I don't get 1. So it's not going to be C. If I plug 0 in here, that works. If I plug in 0 here, that works. So far, I have eliminated options A, B, and C. Now I'm going to debate between D and E. So if you notice, one of the first things that stuck out to me is that it looks like every single little slope mark that's going along the x-axis, they all look exactly the same, which means that it doesn't matter what x is, that doesn't affect the slope. Only the y value affects the slope, kind of like in number 1 where we had 1 over y and only y determined the slope. So that actually tells me right away, if you notice that the answer here is going to be E because y is changing the slope. But let's pretend that you didn't notice that. I'm going to pick another point like this one. That is the ordered pair 1, 0, and that looks like it has the exact same slope. So if I plug 1, 0 in here, I should get that 1 equals 1 plus the x value, which was 1, and that's not true. So that means that it can't be D, and the correct answer is going to be E. So if you're looking at a slope field, look for the key things. Is there a value that it can't be? Is what's happening when x is 0? What's happening when y is 0? And maybe identify a couple of points and the slope at that point and use that to narrow down your options. Okay, so let's recap what we covered in this video. We talked about how a slope field is a visual representation for the solutions of a differential equation and how we can use that to sketch curves so we can get an idea of what the solution looks like. We talked about how slope fields are most commonly used to help us approximate or to get an idea of what's going on in a differential equation that we can't solve using the method that we learned in the section before this. However, it still works with problems like we had done in the past, and we reviewed how to solve differential equations using the separation of variables. And lastly, we looked at a slope field that had already been given to us and identified the slope at some particular values or some particular ordered pairs so that we could narrow down options for what that is the slope field of, what the differential equation is that's being graphed there. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.